Venous return in aquatic animals like fishes is pretty straightforward, mostly because fishes are surrounded by a fluid, water, that has roughly the same density as the blood. This means that the blood of a fish in water has essentially no weight per se, although it does have mass. When we look to terrestrial animals, where they are immersed in fluid, air, with a much lower density than bloods, this means that blood of an air-dwelling creature has weight in a way that blood in a water-dwelling creature does not. This makes the analysis of venous return a little more complicated, which means we need to establish some of the basic physical principles that apply to moving fluids. The most important of these physical principles is known as Bernoulli's law, named after Daniel Bernoulli, the famous 18th century Swiss physicist. Daniel Bernoulli was a member of a distinguished family of mathematicians and physicists, notably his son, Johann Bernoulli, who was important in the development of the calculus. Bernoulli's principle is basically a variation on the principle of conservation of energy. Here it is in an equation. It relates the energy density of a parcel of fluid, E sub F, as the sum of three alternate forms of energy: pressure, P, the gravitational energy, which is the product of the fluid density ρ, the gravitational acceleration g, and the height of the parcel h relative to some equilibrium state. This is the fluid's weight. And the fluid's kinetic energy, which is the product of 1/2 times the fluid density times the velocity u squared. Because this is an energy density, all terms have units of joules per meter cubed, and as I've mentioned before, joules per meter cubed is dimensionally equivalent to the units of newtons per meter squared, or pressure. We can also express Bernoulli's law in units simply of joules by multiplying all the terms by the volume of a particular parcel of fluid. Here, the density terms in the gravitational energy and kinetic energy components are simply converted to the mass of the fluid parcel. Either form of Bernoulli's law expresses the same basic idea, though. Fluids contain a certain energy, which can be distributed into multiple forms. The energy can be distributed among these forms in any number of ways, but they all must add up at the end. Energy must be conserved. Take energy from one form, and it has to show up somewhere else in another form. Let's illustrate this concept with a simple physical system, a U-shaped tube containing a liquid filled to a height h. We'll set zero height at the bottom of the tube, and here's Bernoulli's law. We can simplify this. Because the fluid is not moving, the kinetic energy term can be ignored, leaving only the pressure and the gravitational energy terms to consider. Let's look at the gravitational term first. At the bottom of the tube, where the height is 0, the gravitational energy density there is nil. Moving higher and higher in the tube up to the top of the parcel, the gravitational energy increases as height increases until it reaches a max at the upper surface of the liquid. Turning now to the pressure term, we see that the pressure at the bottom of the tube is maximized, and the pressure at the top of the liquid column is nil. Just as a point of vocabulary, this particular kind of pressure is known as a hydrostatic pressure because it applies specifically to liquids at rest. What Bernoulli's law is telling us is that the sum of the hydrostatic pressure and the gravitational energy density must everywhere and always add up to a constant value. Here I want to digress for a moment to make an ancillary point. The assertion is often made that fluids always flow from regions of high pressure to regions of low pressure. I've made that assertion myself several times, in fact. But we see from Bernoulli's law that this is not always true. In the example here, the hydrostatic pressure at the bottom of the tube is definitely higher than the hydrostatic pressure at the top of the liquid column, but there's no continuous flow from the bottom to the top. The fluid is still. I've made this digression mainly as a cautionary tale about vocabulary. We have to be careful when we speak about pressure because it's only one form of the energy that can be contained in a fluid. In this instance, the fluid is still because the pressure is balanced against gravity. Okay, let's get back to our U-shaped tube. Let's perturb the system a bit. We do work to push down the fluid on one side, which pushes it up on the other. And this leads to a peculiar situation. If we divide the fluid parcel into two halves, we see that the gravitational energy density on the right side is greater than the gravitational energy density on the left side. We have here a situation where we've done work to push this fluid parcel out of its equilibrium energy state. Equilibrium is the level at which the differences of height on either side are nil. When we do work in the system, we impart a potential energy difference to the fluid that is proportional to the height difference delta H. To sustain the fluid in this out of equilibrium state, this difference of gravitational potential energy can be met with an equal opposing pressure difference, delta P. This is the principle of the manometer as a means of measuring pressure. Keep this principle in mind, for we'll use it again when we talk later about the concept of the osmotic pressure. Suffice it to say for now that without this opposing potential energy, the difference of gravitational potential energy will do work on the fluid to restore it to its equilibrium position, that is, restoring levels on both sides of the tube to equal heights. Okay, we've seen what Bernoulli's law tells us about energy in static fluids. What about moving fluids? Here things get a little more complicated and in some ways paradoxical, but Bernoulli's law explains it all. Let's start with a horizontal tube through which fluid flows. Let's make the tube uniform in diameter for now, and let's set in place vertical tubes along its length so that we can measure pressure along it. We're measuring pressure manometrically, of course, that is, by measuring the height to which the fluid is elevated. As fluid flows along the pipe, we see that there's a regular drop of hydrostatic pressure. We already know this from Poissier's law, and we already know the explanation. The decline of pressure represents energy that is lost from viscous interactions between the pipe wall and the fluid that are dissipated as heat. And as the energy is dissipated, the pressure declines. Okay, so far, so good. We also know that the velocity of flow in this uniform pipe is going to be uniform along its length. This is simply the principle of continuity at work. But what happens if the pipe diameter changes? This is where things get interesting. We know also from the principle of continuity that the volume flow rate through the narrow bit has to be equal to the volume flow rate through the wider bits. But because the diameter in the middle is smaller, the cross-section area of the pipe there will also be smaller, and this means that the velocity of flow in the pinched region will be faster than on either side. If we now measure the pressure drop, we see a surprising thing. Pressure still drops along the tube's length, but the pressure at the narrow point is lower than we expect it to be. That seems paradoxical. What's going on? Fortunately, Bernoulli's law has the answer. First, let's simplify things a bit again. Because the fluid is flowing horizontally, we can now treat gravitational potential as negligible. Total energy now is the sum of the pressure and kinetic energy density. Comparing flow in the narrow section of the tube with elsewhere, we see that velocity there is faster, and this has the effect of increasing the amount of energy in the kinetic energy term. But Bernoulli's law says that total energy in the fluid must be conserved, and this means that the increase in kinetic energy has to come from somewhere. Where it comes from is the only place possible, that is, from a reduction of potential energy in fluid pressure. Thus, we have the seemingly paradoxical result that increasing the velocity of flow through a tube results in a net reduction of the fluid pressure acting on the tube wall. This reduction of pressure, what amounts essentially to an internal suction pressure, will be very important in helping us understand how blood flows in veins. Okay, remember Bernoulli's principle because it's going to be very important in helping us understand the dynamics of Venus return. Let's now return to that.